Hi, Mr. Sapone here, and I'm bringing you a screencast on chemical bonding. So we're going to look at some chemical bonds, see why atoms join together, how they join together, how to predict which atoms will join together, predicting chemical formulas. So chemical bonds can be broken into three types: covalent bonds, ionic bonds, and metallic bonds. And covalent bonds can be subdivided into two separate categories of their own. It can be polar covalent or nonpolar covalent. This screencast, for the most part, is going to stick with ionic bonding, but we're going to talk a little bit about all three bonds for a minute. Then, of course, you have another type of bonding called intermolecular. If we had H2O, which is, of course, water, you would have two hydrogens bonded with an oxygen. These would be your hydrogens, hydrogen. This would be your oxygen. Now, water is a polar covalent bond, but water molecules themselves can be attracted to other water molecules through these things called hydrogen bonds. And that would be an example of intermolecular bonds. So after we talk about metallic bonding, ionic bonding, and covalent bonding, we'll talk about intermolecular bonding. For now, we're going to stick with ionic in this slide and talk a little bit about all three in general. So covalent bonds are going to occur between two nonmetals on the periodic table. Ionic bonds generally are going to occur between a metal and a nonmetal. Metallic bonding, well, that one's really easy. Metals. If you have a big pile of aluminum, all those aluminum atoms are metallically bonded, and we'll talk about metallic bonding after ionic bonding. In covalent bonds between nonmetals, the valence electrons are going to be shared. You're going to share valence electrons. That's how these atoms are going to come together. In ionic bonds between a metal and a nonmetal, valence electrons are going to be completely transferred. Sometimes we say stolen to try to get you to remember it better, or transferred, stolen. But that's what's going to happen. Electrons are going to go from one atom to another, and they're going to join together. In metallic bonding, we have kind of this overlapping sea of electrons, this valence shell model, and we'll talk about that when we get to it. But for now, these are the three types of bonds, and this is how the general process works, and we'll look at each one of these in depth before everything is said and done. And this is the periodic table. Remember, metals are on the left, non-metals are on the right, except for this little guy over here. This is kind of an oversight in whoever made this graphic that I kind of stole from Google Images. But hydrogen, it does have one S1. It has one valence electron, so it belongs in this column, but it is not a metal. It should be yellow. It is a non-metal. So let's look at some examples. And we see that covalent bonds are between non-metals. Two elements in yellow. If they bonded together, it would probably be a covalent bond. A ionic bond is between a metal, one of these elements in blue, and a non-metal in yellow. So if we had something like this is the ball and stick model for sucrose or table sugar. If you have 12 carbon atoms bonded with 22 hydrogen atoms and 11 oxygen atoms, you would have one molecule of sugar. What type of bond is this going to be? Well, carbon is a nonmetal. Hydrogen, incorrectly labeled here in blue, is a nonmetal. Oxygen is a nonmetal. Covalent bond. What if we had something like barium chloride? Two barium atoms bonded together with a chlorine atom. Well, barium is over here. It is a metal in blue. Chlorine is a nonmetal. So this would be an ionic bond. And that's what we're going to spend the rest of this slide talking about. In order to understand ionic bonds, you really need to understand Lewis dot diagrams. And what is a Lewis dot diagram? Well, it's just a way of representing valence electrons. Neon is in column 8A of the periodic table, and it has 8 valence electrons. Remember, the column number indicates the number of valence electrons for columns 1A through 8A. So Lewis dot diagrams only show valence electrons. Bohr diagrams show all the electrons in the atom by energy level. this first energy level. This is energy level 1, and that's our 1s2. This one right here is energy level 2, which has a 1s2 and a 2s2, and again we got energy level 3. Same thing, 1s2, 2s2. Oh, sorry. This should be 2p6. Energy level 2 is 2s2, 2p6. This is going to be 3s2, 3p6. And of course, you could go following the Aufbau diagram 4s, 3d10. But for the most part, a Bohr diagram is going to list electrons by energy level. It's going to list them all. It's going to draw them all in terms of these concentric circles, and each circle represents an energy level. And also, we need to understand the electrostatic force. And if you're in my class, you should. And this is Coulomb's law, inverse square law. Simply, all we need to know now is that opposites attract and like charges repel. If these represented two protons, both with a +1 charge, positive charge, they will repel one another. Like charges repel. These are both electrons. Two electrons, they both have a -1 charge. They're going to repel one another. And again, if you had a proton and an electron, opposites, they will attract. So that's kind of how the electrostatic force works. And that's really, we only need to know that to get through ionic bonding. The last thing we need to know is the octet rule. And the octet rule is useful for the first 3 periods or rows in the periodic table, kind of the first 18 elements. And it says that atoms try to attain the nearest noble gas configuration. These atoms are going to lose or gain electrons until their valence shell is full or has the same number of electrons as a noble gas, which is going to be, of course, 8. Atoms with a full valence shell are stable. So we're just going to say that for simplistic purposes, atoms, the octet rule, they want to be like the noble gases. Neon, 8 valence electrons. All the elements in column 8A have 8 valence electrons. Fluorine is in column 7. It wants to be like neon, so what does it want to do? It wants to gain 1 electron. What does oxygen want to do? Well, it wants to gain 2 electrons. And nitrogen is going to, of course, want to gain 3. And this would obviously be a 2p6 if it gained 3. We have the same configuration as neon. So that's generally the octet rule, is saying that atoms want to lose or gain electrons until they're like the noble gases, until they have 8 valence electrons. And it works really good for the first 18 elements or so. So now we're going to look at argon, which is element number 18. It has the electron configuration of 1s2, right, that's right there, 2s2, 2p6, the second energy level, and 3s2, 3p6, 8 electrons in the third energy level. Argon has 18 electrons, which all have a -1 charge. So the total negative charge of this atom is -18. It also has 18 protons in the nucleus, which means it has a +18 charge. The overall charge of argon is going to be 0. It has the same number of electrons as protons. And if you look in this valence shell, there's 8 electrons out here. This is the octet rule. Atoms kind of want to be like argon. So let's look at chlorine, and what makes chlorine different from argon? Well, chlorine has 17 protons, argon has 18. Chlorine also has 17 electrons, argon has 18. Chlorine is in column 7A. It has 7 valence electrons in the shell. What does chlorine want to do? Well, it wants to gain an electron right here. It wants to gain 1 electron to be full. That's what chlorine would like to do. So if chlorine gains an electron, it will now have the same electron configuration as argon. Went from 3p5 to 3p6. It gains an electron. It now has a noble gas configuration, 8 electrons in its valence shell. So now what can we say about chlorine? Well, this chlorine ion, or chloride, has 18 electrons, which has a -18 charge. It has 17 protons still. Remember, proton number does not change. Otherwise, it would not be chlorine anymore. which gives us a plus 17 charge. The overall charge of this atom is going to be a minus 1 because it gained an electron. It gained a negative charge. And let's look at now a nonmetal. Let's look at a metal, sodium. We looked at a nonmetal. Sodium, of course, is number 11 on the periodic table. It's in column 1A, has one valence electron. So how could sodium have a full outermost energy level? Well, you might say, well, sodium can gain 7 electrons. 3, 4, 5, 6, 7. But this is generally not going to happen. There's a lot of electron shielding here, and only a plus 11. It's going to be really hard for this nucleus to attract 7 additional electrons and hold them there with this level of shielding. Really, there's an easier way for sodium to have a full outer shell. That would be just by losing this electron. Instead of gaining electrons, it can lose this. If it loses this, this whole shell disappears, and we're just left with this full inner shell. That's kind of what happens. If sodium loses that electron, this electron right here, it loses it as a 3s1. That 3s1 is gone. It loses its electron. Now it has a full outermost energy level. And again, you can say now this sodium atom has 10 electrons, minus 10 charge. Still has 11 protons. Proton number cannot change. That's a plus 11 charge. The overall charge of this metal is going to be a plus 1. Sodium will lose an electron. And once it does lose that electron, it's going to be exactly like neon, as we're going to see. Neon has 10 protons, 10 electrons. Neon's going to have the exact same electron configuration, the exact same setup. This is the electron configuration for neon now, as we're going to see in the next slide. So again, sodium became just like neon. Same exact electron configuration now. Sodium lost. This was basically sodium. Sodium had 1 electron out here. There was 1 electron out here, and sodium was a plus 11. Sodium lost this single electron, and then it became just like neon, except for obviously the nucleus. The nuclear charge does not change for an element. But that's what happens with sodium. It loses an electron. And now let's look at another example, magnesium. Magnesium is in column 2A in the periodic table. Now you might say, well, magnesium can gain 6 electrons. Again, with this level of shielding and this pull of the nucleus, it's not really going to gain 6 electrons. It's going to be much easier to lose 2 electrons. If it loses 2 electrons, this energy level is going to be completely gone. So what happens? This next energy level, which will now be the outermost energy level, will be full. It will have a noble gas configuration, the same as neon. Magnesium is going to lose these 2 electrons. It's going to become exactly like neon. It wants to be like the nearest noble gas. That's the Octet Rule. So again, this is our neon atom that loses 2 electrons. It is now like, or this is our magnesium atom that loses 2 electrons. It's just like neon now. And what can we say about the charge of this atom? Well, it has 10 electrons for a minus 10 charge. All these negatives, there's 10 of them, minus 10 charge. Still has its 12 protons, that can't change, for a plus 12 charge. So the overall charge is going to be plus 2. So it's going to be a plus 2 ion. And we can kind of make some predictions by looking at dot structures for elements. All of these elements in column 7, they're all going to want to gain 1 electron. They're all going to want to gain 1 electron. If they all gain an electron, they're going to each be like the noble gas to the right of them. Going to be like the nearest noble gas. So they're all going to end up having a minus 1 charge if they form ions, all the elements in this column. Because they're all going to want to gain 1 negative charge. What can you say about these atoms? In column 6, well, oxygen is going to want to gain 2 atoms, or 2 electrons. Sulfur, same thing. Selenium, same thing. Tellurium, same thing. 2 electrons to become like the nearest noble gas. And these would all have a negative 2 charge. Nitrogen is going to want 3. Phosphorus is going to want 3. So we're going to say in this column we're going to have a +3 charge to become like the noble gas. Lithium, if it loses this electron, it's going to have the same electron configuration as helium. It's going to be like the nearest noble gas going that way. Sodium, if it loses its electron, it has 11 to start. If it loses it, it's now going to have 10. It's going to be exactly like neon. Potassium, if it loses its valence electron, it's going to be exactly like argon. And these all elements are going to want to have a +1 charge, right? They're going to lose 1 electron. These atoms in here, same process, but they're going to want to form a +2 charge. And these atoms in general, we'll say, will be a +3 charge. The atoms in the middle are going to be a special case. They're not going to gain or lose 4. They're probably going to share electrons and be covalent bonds. But we'll talk about that later on. So this kind of shows what we just dissected. If you were to look at the ionic charge by column, these are generally going to form +1 charges. +2 here. And these transition metals and all these in the middle, they're special cases. We'll talk about them. I'll give you a chart. They're based on electron configurations. As you get in here, you could have different configurations and different shells full for stability. And again, we saw this already, +3. Special case to 4, column 4A. These atoms all want to gain 3. These atoms want to gain 2. These atoms want to gain 1 to become like the noble gas. So that's how our ionic charges are going to work. And now just to make sure, let's formally define ions. An ion is an atom that has lost or gained electrons. Metals are going to lose electrons and form positive ions. That should make sense now. Atoms on the left in the periodic table are going to lose those electrons, so they're going to become positive. Nonmetals are going to gain electrons, and if they're gaining negative charges, they're overall going to become negative ions. And 2 words you just have to memorize: cation and anion. Cations are positively charged ions. These are metals that have lost electrons. Anions are negative ions. These are going to be the nonmetals that have gained electrons. And the easiest way I can think of remembering this is to say that cats have paws and cations are positive. Kind of simple, but it does work. The other ways you can think of that, there is a T in the word cation, so plus, positive charge, cation. Another way, a student actually taught me this one, anion, kind of looks like the word onion with an O instead of an A, and onions of course make you cry, so they are negative. So I guess those are 2 ways you can kind of remember it. Both are remotely funny, kind of like this little critter right there. So now we have all the groundwork laid, we can talk about an ionic bond very simply. Sodium is a metal. Chlorine is a nonmetal. A metal and a nonmetal join, that is going to be an ionic bond. Sodium has 1 valence electron. It wants to lose that electron. If it loses it, it'll become like neon. Chlorine, number 17 on the periodic table. It wants to gain an electron. It'll become like argon if it does. It'll be happy. It'll have 8. Sodium have 8 because it's previous level. So what's going to happen? Well, sodium's valence electron is going to be transferred to chlorine. Wonderful. Sodium is losing its electron. So what's the charge going to be on this atom? It should be positive. Chlorine is gaining a negative, so its charge is going to be a negative. So sodium becomes a cation. Remember, metals form cations, an ion with a positive charge. Chlorine becomes an anion, an atom with a negative charge. So once this whole electron transfer is done, sodium's happy, but overall it has a positive charge. Chlorine is happy, but overall it has a negative charge. What do opposite charges do? They attract. Yes. So what happens is the sodium ion, right here, positively charged sodium atom, after it loses its electron, it's going to combine with the chloride ion. Because opposites attract. Chlorine gained an electron, it's negative. Sodium is positive. Due to the electrostatic force, Coulomb's law again, these 2 atoms are going to come together, and that is known as an ionic bond, electrostatic attraction. So to summarize, ionic bonds, valence electrons are transferred. Valence electrons are transferred from one atom to another. This sodium is going to give chlorine its valence electron. They occur between a metal and a nonmetal, sodium, chlorine. Metals are going to lose electrons. Sodium is losing its electron. It's going to form a cation. They have a positive charge because cats have positive and they're positive. Nonmetals gain electrons. They form anions. This chlorine is gaining a negative particle. It's becoming negative. And then once you have a positively charged ion and a negatively charged ion, cation, anion, they are going to electrostatically attract to one another. That is an ionic bond. And just to drive home the point, we're going to look at one other example. Lithium is a metal in column 1A. Fluorine is a halogen in column 7A. Has 7 valence electrons. Lithium has 1. What's going to happen? Lithium is going to donate its 1 valence electron. It's going to transfer it to fluorine. And then what's going to happen at this point? Lithium is going to form a cation with a +1 charge. It's going to be a +1. Fluorine is gaining that electron. It's going to be an anion with a -1 charge. And again, opposite charges are going to attract. They're going to come together. These two atoms are going to join. And we're going to call them lithium fluoride. So you can kind of look at the periodic table and predict a lot of combinations of elements based upon ionic bonds. A lot of the elements in column 1 are going to combine with the elements in column 7A. Elements in column 2A are going to combine in column 6. Elements in column 1A are going to combine with elements in column 6 in different ratios. So you can kind of predict some chemistry now, understanding how an ionic bond works. And just to finish up, you're going to have a brief assignment. I want you to draw an illustration of an ionic bond forming between potassium and fluorine. Again, it's a simple column 1 and column 7 element. Just show me how it works. Make sure you understand this video. And I want you to explain the pictures in the following 4 slides in your notebook. I don't need a thesis for them. Just tell me that you understand what they mean. They're supposed to generally be funny images. So we have image 1. Explain this picture. What does it mean? Why is it funny? Explain this picture. What's going on here? Explain this one. Name is bond, ionic bond, taken, not shared. And the final image is a little comic strip by Blackbird. So explain these 4 things. That's your assignment. Show me an ionic bond between, I believe, potassium and fluorine, I said. And hopefully you have a good understanding of ionic bonds now. Mr. Sapone, I'm out.